And so let's remember this problem that we did a while back where the matrix A was 0, 1, 1, and 0. Right? And so, what do I want to highlight? Let me grab the important thing. We've done this problem, and after doing this problem, we set up its eigenvalues, we set up its eigenvectors, we get the solution. Here is my solution. I'm going to erase some tidbits here. This is my general solution right here. Okay? What we want to do over here on the right-hand side is graph this solution in the x, y plane. Okay? So, I look at my A matrix, I go upper left times lower right, which is 0, minus lower left times upper right, which is negative 1. Since the determinant of the A matrix is not 0, there is an equilibrium point and only one equilibrium point, and that is the origin. So the origin is going to be my equilibrium point. Okay. Next. How am I going to set this up? I'm going to use purple to denote this eigenvector with C1 as the multiplier. Okay. I look at this eigenvector. It says go 1 in the horizontal direction, 1 in the vertical direction. I get this point right here. And so this is my eigenvector. Okay. So I will actually just make the eigenvector purple, and then I will talk about the influence of the green part. This 1, 1 is my eigenvector. C1 is any multiple of it. So what happens when I take this eigenvector and I multiply it by any real number? Well, if the real number is positive, it's just going to still go cooking off to the upper right like this. But if C1 is negative, it's going to take this vector and bust it into quadrant 3, but then any negative multiple makes a continuation of this line in quadrant 3. And I would call this the first eigenline. Okay. Now with this first eigenline, because of this exponential on this first eigenline, which I'll highlight in orange, what does that exponential do? Say you were a styrofoam peanut and you were dropped in right here where the cursor is, right? Then that e to the t is going to multiply onto the C1, 1, 1 vector. And what's that going to do? That's going to cause growth in this direction. It's going to take the styrofoam peanut and it's going to multiply by this growing exponential, and it'll say, hey, just continue on in this 1, 1 direction. Okay. Now, I come over to this second eigenvector, which is 1, negative 1. So it's a vector right here. I'm going to eliminate actually the arrow. I'm going to eliminate its arrows. So there's my second eigenvector, but now C2 is a multiplier to that second eigenvector, so I'm going to color that in brown. And if I multiply this by any positive number, it'll just scale this pink vector, make it longer. Like this. And then if C2 is negative, it'll bust it into quadrant 2 and negate everything so that there's a continuation of this vector going into quadrant 2. So any multiple of this vector right here makes this second eigenline. And then because of this exponential, if I multiply this anything on this eigenline by this exponential right here, well, this exponential is decaying. That decay is going to be seen as arrows pointing inwards on this eigenline. And so this is the plane where what I've done is I've plotted both of these eigen solutions and just the lines associated with the eigen solution. So if I pretend C2 is 0, I only have this first solution. This first solution forms this green line, and because of this growing exponential, there's growth on this green line. And then if I pretend C1 is 0, so I've got an initial condition such that C1 is 0 and only C2 stays, I get this brown eigenline. And because of the decaying exponential, I see decay on this brown eigenline. And so what I've done is I've set up the entire plane to be scaffolded off of these two eigenlines. Okay. Questions about that? Now, if styrofoam peanuts on the brown eigenline go to the red equilibrium point, this is like a phase line that's a sink. If this first eigenline, if styrofoam peanuts are on this first eigenline, arrows point away from the origin, so it's a source. What do solutions do out here and in these four regions that are cut up by these eigenlines? Well, first, we want to make the following notes. As t gets very, very big, that's my language now for t being very, very big. If t gets very, very big, I'll tie in the question in chat right now about the arrow directions to what's going on right here with my solution. If t gets really, really big, tell me, what does e to the negative t do? It gets really, really small. And then e to the t gets really, really big. So if t were a really big number, wouldn't x just be approximately c1, 1 e to the t? Which I'll highlight in brown because that's associated with, or purple, because that's associated with my, or green, sorry, green, because that's associated with my green eigenline. Now, let's run the reverse argument. If t is much, much less than -1, it's a really big negative number. If t is a really big negative number, what happens to e to the t? It becomes a really, really
small number.
Yeah, totally, right? And if this e to the t, this orange e to the t becomes a really, really small number, the e to the negative t will become a really, really big number. And so my x is approximately equal to c2, 1 e to the negative t, which I've denoted is my brown eigenline. So what I'm seeing now is that for really, really far back in time, my solutions need to look like the brown eigenline. So they're behaving a lot like the brown eigenline. But as I go really, really far forward in time, those solutions transition to the green eigenline. So what would my solutions do? Really far back in time, they should be like this brown eigenline. But as I go forward in time, the brown eigenline's drawing me into the origin. But as I get closer to the origin, I realize there's this green eigenline that's pulling me away. And so I get a solution curve that looks like this. In fact, I get many solution curves that look like this. And then what would happen in this upper region? Well, really far back in time, I have this brown solution curve drawing me in, but then as I get closer to the origin, I see the green solution and it's pulling me away. And then brown deep in the past, going forward, I meet green. Green pulls me away. Brown far in the past, green pulling me away. And of course there are many solution trajectories for each of the four regions. Here I show that but then I just do 1 in each of the other regions. And so this intersection of a phase line which is a source with a phase line that is a sink is called a saddle. 0, 0 is a saddle. Now what can change about this saddle? Well, the eigenvectors could change, and what would happen is that the eigenvectors might make not 90-degree angles, but acute and obtuse angles, but that I know one eigenvalue is positive and one eigenvalue is negative, I know one eigendirection will draw me in and then the other eigendirection will repel me away. So that's what I meant when I said all we really need to know are the eigenvalues. If I want to draw this actual picture, I need to know the positioning of the eigenvectors, but if I change those eigenvectors and keep the eigenvalues the same, it's just going to change the acute and obtuse angles in the eigenlines. Okay? And so now I will get set up. I'll fade away, and you can take any last notes you want there. I'll freeze, and I will get set up a visualization that will hopefully draw all this together. So I'll go full screen, and then I'm going to transition to the graph in 3, 2, 1. Brooke is asking, what does the greater than symbol and the less than symbol mean? It means really big or really small, because in the limit, things either go to infinity or things go to infinity. And so if I don't want to write a limit there and I want to talk about big and small, that's the notation that I use. So here is a visualization of exactly those styrofoam peanuts. And what am I seeing? I drop a styrofoam peanut in. It gets closer to the origin. But as it gets closer to the origin, it feels the second eigenline, which is a source, pulling it away. And the trajectories we were finding, the solutions we were finding, are the curves that are traced out by this myriad of styrofoam peanuts being dropped into this vector field. Okay. So that is going to be it for today.
The recording has stopped.